This is not going to be a very technical talk. It's going to be more of a story. I think this is something that we have decided when you first invited me. You can relax. So I'm just going to tell you a story, not too technical. Right. A bit about myself. I think it's already in the bio. So I got my PhD in Turkey, and then I did a postdoc in Canada, Siralt, and then 3 years in Istanbul as an assistant professor. Then I've been in the UK for the last 9 years, lecturer, and then reader, and then professor for the last year and a half. So how it all started. I was, as they call it, an ivory tower academic. So I would like to just do my theoretical work and write my own papers. Then at a certain point in 2012, there was an opportunity. I was working at the University of Southampton at the time. The opportunity was to work with Oxfam. If you have never heard of the name before, Oxfam is a charity in the UK. So they help people in need. So how do they do that? So essentially, when you have used something for long enough and you believe that it's not too much valuable for you, but it may be valuable for somebody else, like clothing or books or CDs or DVDs, you give them to Oxfam, and then Oxfam either recycles it if it's not in a condition to be sold again, or they have shops, so they sell what you give them after cleaning them and properly organizing them in the shops, and they make money out of that one, but they don't make any profit. Whatever profit they turn, they give over to people in need. So it's a charitable organization. These organizations don't exist in Turkey. It was quite a mystery for me how they were, but apparently it's the form of charitable organization in the UK. So it is much more organized here. So Oxfam decided to install some charity collection banks, as they call them. The name is bank, but what it is it's actually a big garbage bin. So and it is also a smart garbage bin, what they were installing. This was 8 years ago. So there are sensors in it, and the sensors are showing how much of the volume within the box is occupied. So as people are putting their clothing and then their old books and all CDs and DVDs inside, it is measuring it, and all these measurements from all these places all around the UK, and I'm speaking about hundreds, they're all coming to a centralized IT system so that you have an idea of how much is accumulated where. Now, the catch is, this is not garbage. This is actually things of actual value. So if somebody finds a DVD on the road next to an Oxfam bank, and they seem to like the DVD, they will pick it up, no problem. I mean, you just wipe it off with a disinfectant, and you can use it, right? So because of the economic value, you don't want to lose anything, and they did lose things because they overflow. So if the box is full, and then a new donation comes, well, whoever brought the donation won't bring it back. They will just leave it next to the box, and then whoever comes for collection, that's their problem. And then whatever is left next to the box usually goes away. It's not charity anymore. Somebody else took it for themselves. Okay, so what do you want? We asked Oxfam, and Oxfam said, we need some sort of an algorithm that is going to tell us, when we point out this is the situation, what is the most profitable or actually least costly way of collecting the contents in these boxes based on the fill ratios of these boxes. Okay, makes sense. So I had some code. We were in a hurry. I had some code, taboo search code from traveling salesman problem variants, and because we were in a hurry, I couldn't develop a full proper algorithm, to be honest, and they were not interested in. They just wanted an algorithm that was going to do what they need in a quick manner. So we adapted it, and we did give them an output in the end, and they were quite happy with it. And there was some experience in the meanwhile, because I never worked with these charitable organizations anymore. So what I learned was vehicle routing in theory was like the picture on the left, the white truck, all nice and clean and well loaded, and you can tell it where to go and it will. And this is very much like the way I used to start my papers. Let us define a network G with vertex set A and arc set vertex at V and arcs at A, and demand Qi associated with each I in V. Well, it doesn't work that way. So as I started working with these people in Oxfam, I understood that vehicle routing was nothing like that in actuality, in reality. So then I moved over to my current university, from University of Southampton. And I'm working in a department, and I'm surrounded by people who do research and operations management. So operations research in the UK is not housed in industrial engineering, it is housed in management, mostly. And 4 or 5 universities, it is in the School of Mathematics, but the rest it's in the School of Management. And when you're surrounded by people in management, I mean, they are still quantitative people. They have a quantitative way of thinking. But once you mention ERP to them, they stop. Why? It's intimidating. It's a very complex problem. There is too much data involved. The algorithms involved are way beyond their capability, or at least they think that way. I mean, if you start speaking about meta-heuristics, they freeze. Or you start saying something about branch and cut, no, that's too much. So it needs to be simple. So these people, operations management people I'm speaking about, they need it simple. If it's not simple, it's not implementable. If it's not implementable, it's not useful. Okay, so the complexity of the models and the algorithms we use, and the lack of data, and the lack of a standard tool was stopping them from using this sort of models. Lack of data is the other thing, that we ran into the same problem with Oxfam. So they wanted to know the shortest paths, the minimum cost, and that was based on the distances, but they didn't have the distances. So it's very interesting. They want to solve a problem, but they don't have the data yet. And also, so they wanted to see how well they were doing with respect to before. They didn't have a tool before. So there was no basis of comparison. So you give them a route saying that this is a good route. They don't know if it is good. They don't know anything else to compare it with. They have what they had before, and what they had before is not quantified. It's just the sequence of boxes that they were visiting. They didn't know how much distance they were actually traversing. So this kind of gave me an idea. It's more like the picture on the right. So the vehicle routing in actuality is more like the right. So it's quite dirty, and it needs to be simple. It just needs to get the work done, and quick and dirty, and not necessarily in an optimal way, in a good enough way. Okay. Once you get the good enough, then you can get the better, and maybe hopefully one day optimal, if at all possible. Right. So the second step, what I learned from working with these people in Oxfam is, one, all data should be kept in Excel. So in my experience as an academic, I was keeping my data in text files. Why? Because it was easy. You double click it, it opens. Or if you're in Linux, you just open it with a simple editor, and you can just read it. Okay, all is good. No, I mean, they don't want to. They want to see it in boxes in an orderly manner. So that they can do simple analysis on it. What is the maximum full box at all time? And what is the most used bank? I mean, small, simple analysis can be done very easily with Excel. So they want to keep all data in Excel. Okay. The second point was, when I was designing a meta-heuristic as an academic, you could run it for 15 minutes, half an hour, 1 hour, 4 hours, maybe. You report all of them, showing how the performance improvement is marginal after a certain point. No, they're not going to spend more than 10 minutes of CPU time. I mean, at least this is the set of people at Oxfam I'm referring to, but I think this is the general mentality, general mindset of practitioners. So what they can do is they can load the data, they can press the button to solve, and then they can go and get some tea or coffee and chat for a few minutes. But once they are back, they need to see something. You cannot tell them, there's a sophisticated algorithm working in the background. It's going to take the whole CPU power of your computer for 4 hours, and then when you come back, maybe it's not a good solution as well. Well, that's not going to work. So they need something that is going to work within 10 minutes of CPU time. And I used to envision that the output of the algorithm, wow, this is beautiful. Let's do this. No, it doesn't work that way. They need to see it. They need to understand it. There's a human element, right? They need to make sure the solution actually makes sense before giving it out to the drivers and implementing it. Otherwise, they are the ones responsible for it. The output of the algorithm is not the output of the decision-making process. it is the input of the decision-making process. So whatever you give as an output to the decision maker is probably going to be modified. Why? Well, because the data will have changed. Some vehicles won't be available anymore. Some boxes were giving wrong signals. The sensor was showing completely full, and then one of the boxes inside fell down, and apparently it was only half full. Okay, the data has changed. Or the traffic data has changed. There's an accident on one of the roads, so the trucks cannot use it anymore. So they will decide themselves. They just want an idea, want an option. So what should we do? The other thing is mouse clicks are preferred upon keyboard clicks. They wanted to click things. They want to drag and drop. I mean, entering data into a box was not preferred. Let me put it that way. They would rather just click buttons and pull things around. And final thing, and probably the most important thing, is all results must be visualized. So anything you give in textual form, they will need to read it, understand it, and visualize in their heads. Okay, and there's already an obstacle. They're already inclined to say no. Why? Well, this is a different system. We were not doing this before. There's the psychological component, right? They're resisting change. If you can show them what you're proposing, then it will make more sense, and then they can visualize it in front of them instead of their minds, and then they can modify it and see it again, and then they can modify it until they see something they like, which is not necessarily the best solution or even a good solution, but it looks good. So it had to look good, and for that one, it had to be visualized. So these things kind of changed my perspective about how to do research on routing. So until that point, I was more of a mathematician, I think. So from that point on, I moved towards operations management, seeing how things actually worked. Right. So as I was processing these things in my mind, we organized the Verilog 2013 conference in Southampton. In case you're not aware, Verilog is the Vehicle Routing and Logistics Working Group within the Euro being the OR societies of Europe. So this is a group that used to meet every year. And then they made it every 2 years, and I don't know what's going to happen after COVID, to be honest. But at the time, we had about 120 attendants in Southampton, and we organized the panel. There were 3-4 very well-known academics on the panel, and there was also the managing director of a logistics consulting company. So this person had a lot of experience, and I think he was in his late 50s at the time. He spent a good 15-20 years at least in the logistics consulting company, which is a software company. Essentially, they were doing optimization software. And then he decided to do a PhD. And because of his experience and now his newfound academic experience as well, they decided to put him on the panel. We decided to put him on the panel, actually, as the organizers. Okay. And next to me, as I'm beginning to listen to the panel, is sitting Gilbert Laporte, my co-author, and he's one of the best-known names in the area of vehicle routing problem. And Gilbert turned to me and said, "You attend to one of these panels, you don't need to attend anymore because they always say the same things." Okay, why? Because it's the same questions, it's the same answers, nothing ever changes. But it was a bit disheartening, I'm one of the organizers. I wanted to be a good conference. I want something new. So that got me thinking. So I decided to ask a question to the panel that has never been asked. So I said, so more and more I understand the industry standard for doing this sort of analysis is Excel. Okay, any sort of quantitative analysis, at least it needs to be opened in Excel or shown in Excel. But the data is in GIS. So when you want to minimize distance or cost or driving duration, it's in GIS. And the code we develop is in C++ or sometimes in Java. So it is actually quite cumbersome to get the data from one place, put it into another, and then put it into another. Get it from GIS, put it into C++, and the output goes into GIS. This is cumbersome. Do you think that we could have a unified tool that could put it all together? So the 4 senior academics didn't say a word. They just looked at the managing director of the logistics company, and he just looked at me and said, "You cannot. It's just not doable. Don't bother with it. It cannot be done." And then there's silence, and then there's another question. And I felt, no, that it cannot be that simple. There must be a way of doing this. I thought it was a deep and meaningful question, and it has been regarded as a very simple and not meaningful question, which got me thinking: is that really the case? So I started thinking more and more about that one. I think by the end of the panel, I had already decided that I was going to do something about it because it sounded good to me. So I decided to make a VRP solver that was going to unify the components of data, algorithm, and output all together in a single unified tool. So we OR people, operations research people, we tend to do quantitative stuff, which is very well designed. You start with pre-specified data, you process it, and you give an output. When you try to design a tool, then you need to have principles, right? Because you don't have data, because the tool doesn't exist. For the tool to operate, you need data, but you don't have it. So first you need principles. So the principles I wrote down at the time was, one, whatever you do, it needs to be an extension to an existing or familiar system. Why? Because if you tell the decision makers, okay, I have this beautiful tool for you, but you need to learn it from scratch. Well, no. Okay, we're running a day-to-day business here. We're busy enough. If I would learn, I have a lot of other things to learn. Why should I learn this one? I don't even know if it's going to work. If, on the other hand, it becomes a part of what they do every day, it is just one click away, it is within the environment they want, then you're one step closer to your goal. So that was the first thing. The second thing is it should not require compilation. So there are professors and there are PhD students. I'm sure at a certain point in your career or in your studies, you wanted to use some code from somebody else. So you go there, well, it's code. So first you need to understand where to compile it, okay. And then you import it in, and then the compiler doesn't work. Why? Because certain libraries has to be linked, okay. Where are the libraries? I download the libraries. Are they in the right folder? Okay, are they referenced? Where is the linker? Does the linker work? Okay. I mean, an operations manager or anyone doing the logistics decisions is not going to put up with that one. He's not interested in that one. They are interested in the result. They are not interested in the process or the tool at all. They just want a usable or something that can be converted into a usable result from computer. Should retrieve GIS data. Goes without saying. I mean, if it takes them another 15 minutes to get the GIS data, no, that's not going to work. So it all needs to be within the single box. And the fourth one is it must allow for manual changes on the solution and the feasibility check. This is something I realized based on my even previous experience when I was working at a software company. So I think one of the worst things you can do as an OR person or as an analytics person is to provide the decision maker with a single possibility. Okay, this is what you need to do. No, it doesn't work that way. Then you become the decision maker yourself. So the idea is to give the decision maker either options. Option A, you can do this. Option B, you can do this. Option A is more cost effective. Option B is faster. Or option C, option D. I mean, based on what you can do, 3, 4 options, probably no more than 4. Still, the decision maker won't be happy if they cannot make it fit to their needs. Okay, because as you all know, a mathematical model is a representation of reality, not the reality. And if they don't like something, they want to change it. And most of the solvers I've seen around were just outputting one result, and this is okay, this is it. Although the decision maker will want to modify it, and they want to see if it's still feasible. This route, okay, this looks like a good solution, but this route is too short and this route is too long, and the driver of the long route won't like it. So I'm going to move one of these stops from the long one to the short one. Okay, looks a bit better now. Is it still feasible? So the feasibility check was also necessary, and must allow a visual representation of the solution. I already said that it must be visualized. And it shouldn't be a black box effect. I mean, it shouldn't be a black box. If it is something, it's okay, here's your result, and you have no idea what went in there and what came out and how it worked, it just won't work. So there shouldn't be the black box effect at all costs. So keeping these in mind, I just realized that Excel was the best solution. Why? Because it is used in almost all the world. When I buy a computer from my university with my budget, it comes with Excel preloaded. I don't need to think about it. It also exists on Macs, Apple computers. And so essentially, if it's just a single Excel file, you don't need to install anything. You just need to double click it. And Excel also has some HTTP libraries in there, which would allow it to connect to GIS. And I'll speak a bit more about that one on the next slide. So it is the industry standard for basic quantitative analysis. And it is very flexible within its limits. So think of it this way. I still use Excel in my research. I don't know if you have heard the news, but a lot of developers working for Cplex, they all resigned and they moved over to Groby. And Groby was already quite powerful at this point. I think I'm going to switch over to Groby in the coming years by the look of it. Anyways, Cplex and Groby, they are very efficient tools, but you can only do optimization with them. Think of Excel, I think of Excel as a Swiss Army knife. So it has many small tools on it, and you can do very small, useful things with it. But obviously, you cannot do the things you can do with Excel or Groby. You cannot solve large-scale optimization problems. But there is a very nice feature of Excel, which is Visual Basic for applications. Visual Basic for applications is the building block of Excel, as well as Access and actually PowerPoint and Word. So it is never too far. So if you press Alt and F11, you always see an VBA editor. And in other applications, it is not as useful, but in Access and Excel, especially Excel, it gives you a lot of options that Excel, despite its flexibility, cannot. So it is actually a basic programming language, and it has all the functionalities you need. So when we develop an algorithm, what we need is the for loop, while loop, and if statement, right? I mean, I know that I'm being overly simplistic, but with these three, I think you can code a lot of things. VBA has them and more. So what is the catch? VBA is approximately 3 times slower than C++ for basic arithmetic operations. So this is something that I found in the literature, okay? And I wanted to see for myself. So what did I do? I took the taboo search code that I had and I translated it line by line from C++ to VBA. And I had a set of instances of size 150 vertices that are customers. And I gave it 10 minutes of CPU time in C++ to the taboo search code. And every time it was more than 10,000, 11,000, 12,000, sometimes 10,000 something, but more than 10,000. The exact same code, translated line by line to VBA, was performing around 200 iterations. So VBA is approximately 3 times slower for basic arithmetic operations. So when you're actually performing taboo search, you're reading arrays after arrays. You're reading and writing from arrays. There is a lot of memory management. And apparently, VBA is really bad at memory management, at least not as good as C++, which is possibly the best one. So they're not even competitors. Well, that has to be a catch. Otherwise, we would all use Excel, right? So based on my analysis, I started building the tool. So the first hurdle was the GIS data. So Excel, there are web service libraries in there, which means that you can put together a text in terms of a web address, and you send it to a web service like Bing Maps or Google Maps. And in particular, Bing Maps is what I used within the solver. And it gives you back an HTTP answer, a text answer, saying that this is the route that you asked for, and this is the duration, and this is the distance. Okay, so what can I do with GIS? I started looking into that one. And I'm speaking of the year 2013 now, I think November or so. And I didn't know anything about web services. I mean, I knew about GIS in general, but I never knew how they could be used over the web. And when I started this project, I started with Google Maps because, in all honesty, it's a better one, but it's illegal. it's illegal to distribute code that can repeatedly call Google Maps. Why? Because there's something called a denial of service attack. So essentially, you call the same service over and over and over, you flood it with too many requests, and then it cannot function anymore. So they wanted to make that illegal, so they said that you cannot distribute code that can repeatedly call Google services. So that was not the question anymore, so I decided to use Bing Maps. What do you need for a VRP solver was the next question. One, you need to be able to convert addresses into latitude and longitude, so coordinates, geographical coordinates. Why? Well, when you want to deliver something to someone, you have an address, right? But the address may be wrong, and usually in the background, when you digit this one, when you type an address into a routing software, most of the time it actually corrects the address. I don't know if you have realized. So what the solver does is when you type that in, then it gives you the latitude and longitude, and if it doesn't look right, then the address is not right. So you have to correct it. The second thing is the function is called directions. So this is the actual, think of Google Maps or Bing Maps. When you go from A to B, it says go for 100 meters, then turn right, and then turn left and go for another 2 kilometers. And it gives you actual directions. But that was not what I was interested in, but there was not a single function that would give me just the distance or duration of driving. So directions is the second function. And the last one, the most important bit, if you ask me, for visualizing the results, I needed static maps. So if I was going to deliver something in the UK, I needed a map of UK to be put in the background of the map that I was going to use. Okay, and I looked into it, and Bing Maps seemed to have all of them, so I incorporated that one in as well. So now I want to show you a video that I've done at the time. So this is the console where you enter the data like the number of customers, the type of operation, number of vehicle types, and how much time you want the CPU to use. And there are also some options here that I canceled in the next versions. This is an old version that you're looking at actually. And then comes in a set of addresses that I'm going to use, the first one being the depot. Okay, and then there's already a key in place, so you can just ask the solver to populate the latitude and longitude for you. Okay, now that we know where they are, we need to know the distances and driving duration between them. This will take about 10 seconds. Okay, then we need to know about the vehicles. Let's just say that we have 5 vehicles and we don't have any positive demand, so they all have a capacity of 1. So this is what the solution is going to look like. Sequence of customers for each vehicle. And there are 5 of them. Green is what you can modify in this version. Then it became blue actually. So you can just use the drop-down menus to make a sequence. And then you can visualize this one on a static map. Okay, it looks like this one. So what would be the best way of doing it with minimum cost? So in this case, I give 10 seconds, but obviously, the longer you give, the better result you achieve. So finally, it gives you the sequences. So only 3 vehicles are necessary in this case. Right. So what you have seen was the version from 2000 and I think that was 2013 when I did the video. Since then, there are a number of changes, but the main structure, the spreadsheet structure is the same. Now the menu is a bit more involved. The solver has evolved in the meanwhile, so it became better. And a few other things as well, but the main functionality, the main ideas are still holding true. I want to speak about some applications. So this has been applied, the solver has been applied in Istanbul. I don't know if you have ever been to Istanbul. It's 17 million people. It's a country on its own. Essentially, there are town centers, and each town center is a small city on its own. And this is a governmental health organization that doesn't want to be named. And they are providing nurse services to people who cannot go to health services. So these are poor people with no one to take care of them. So they apply for health services and they send a nurse on a bi-weekly or weekly basis. And these nurses, they have their own cars, and they need to drive and they need to visit these people and come back. So in this picture, the return is not shown actually because it made the graph a bit too complicated. But after the last point they reach, they just go back to the depot to leave the car. And when we started the project together, they said, we don't have any capacity. So why? Because whatever the nurses need, it's in the car. So no matter how many people they visit, they don't use too many materials, so it can fit in. So okay, incapacitated problem. And after a few tries, they realized that there was a capacity, because some routes, when you ask the solver for an optimal solution or a best solution, were coming to be a lot of driving with just a few stops. Why? Because there's a time constraint. It needs to be done within the same day, within 8 hours of working. And some routes were coming out to be little driving, but a lot of patients. And nurses were not happy. They wanted to drive more or less the same amount. They wanted to visit the same, more or less, the same number of patients. Okay, so then we realized that it's actually capacitated. So we didn't want any nurse to visit more than 15 patients per day. I don't remember the exact number, it may be 12 or 10. Anyway, so they wanted to have a way of preventing the nurses, for any single nurse, from visiting too many patients. So we just used the capacity for that one. But in the end, they were happy with it. They did not provide an improvement per se, and numerical value in terms of percentage or money savings. They just said that they were very happy with the result, and I had to live with that one. You can only push governmental people so hard in Turkey, so they were not happy to give me any more information about that one. I was just happy that it was used and it was useful. The other application I want to talk about happened in Finland. So in this map, the upper part is Finland, as the map shows, in very light gray writing, if you can see it, Finland at the top. And what they do is they organize tour from Helsinki to Tallinn, Estonia. That's at the bottom of the map. So essentially, the dark green dots show the customers that have to be picked up, and the light green ones are optional. I did not know exactly why some were optional, so I think this is some sort of pricing going on in the background. Some were priced higher, some were priced lower. Anyways, so they were using the solver to decide the routes and which optional passengers, if they can pick up based on the capacities of the vehicles. You know, early in the morning they depart from the beginning of the route, and they need to be in Helsinki around 10. I think 10:30 the boat departs, so it was going to Tallinn, and then they would be there for lunch, have a lunch, see around the city, and in the evening come back, and then using the same routes they were delivered back. They were quite happy with the result, and they were gracious enough to give me some results. So they said that the savings they were looking at were about 30,000 to 60,000 euros per year, which is not too bad if you think of it, because they didn't pay anything for the software. They didn't use any money for consultancy. You can just go to Bing Maps and get yourself a basic license, which allows you to use to a certain point. You know, and for this size of problem, it's not a problem at all. So they were quite happy with it. I did receive some very good feedback from a few companies, but on the basis that it had to be confidential. One company in the US, particularly, so this is a company in energy, so they were collecting petroleum. They wanted to find the best routes for their tankers, for their trucks that carry oil between the wells and the storage locations. They didn't give me any specifics, but they wanted to solve a one commodity version. So usually in VRP, you deliver or you collect, right? So one commodity VRP is when you collect and then you deliver, and then you collect again, and then you deliver again. So you do it a few times before going back to the depot. which is a slightly different form of VRP, but they wanted it. I implemented it, and in the end, they wrote me a letter saying, well, thank you so much. We have saved about $500,000 per year. Okay, so that is the largest reported savings that I have encountered. I need these things because in the UK, we need to document the impact of our research. So that's what our departments ask us. So there were a few more companies, none of them as significant or as impressive, but I know that for at least one company, it saved $500,000 per year, and the solver itself has been downloaded more than 15,000 times by now. I don't know how many of these downloads actually resulted in an application or saving. So I think with a modest estimate, I would say around 2%, 3%, which also gives you a good number. You know, it's more than 200, 300 possibly implementations with good savings, hopefully. So this is the story of the VRP spreadsheet solver. A few more things about it. So which variants of it can it solve? How many rather than which? So it can be open VRP, where you don't need to return to the depot with your vehicle, or closed one, which you have to. Fleet type can be homogeneous or heterogeneous, so ×2 from that. Optional visits, so with optional visits, it becomes actually the orienteering problem, team orienteering problem. And then time windows, hard or soft. Should there be a distance constraint or no distance constraint? In terms of pickup and delivery, it can be complete the pickup, it can be complete the delivery, or pickup and delivery together. It can also be two commodities, so it can be simultaneous pickup and delivery. Think of it like you're distributing these canisters of gas, right, for domestic use. And as you're distributing them, you also want to collect the empty ones. So that's two commodity. One you're distributing, one you're collecting at the same time. That's two commodity. You can also solve one commodity, like with pickup and delivery, like the case with petroleum. You can go to some wells and get the tanker full, and then you can go to a storage area and empty it, and go to another well, fill it again, go to another storage area, empty, and so 3 types there. When you multiply, it's 96 variants. I mean, the actual number doesn't really matter. What I wanted to do was to make it as flexible as possible. So I didn't want anyone downloading and saying, oh, this doesn't work for me because of this reason. Of course, there are cases, but I try to minimize it. Okay, so how does it work? The algorithm, which is open source, you can just go into the VBA editor and see in the file. It is a large neighborhood search algorithm. There are 2 constructive algorithms inside. One of them is randomized greedy insertion, and the second one is randomized max regret insertion. What it does is it looks at greedy insertion. So first, it's random location removal. That's the distraction heuristic. You take out some customers, and then putting them back, you either use randomized greedy insertion. It looks at with the greedy choice which ones are the best, and from the top 3 it picks one randomly and does it, and the other one does the same thing with max regret option. And then once you complete it into full solution with all the mandatory places visited, it also uses a local search with the well-known local search operators, 2exchange, 1opt, and 2opt. I also added a vehicle exchange in there. This is for heterogeneous fleets. So it is about exchanging 2 routes. So if you have a short route and a long route, and in different types of vehicles, and one of them is cheaper, you can just swap them over, and it will be better. And none of the existing moves, the 2exchange, 1opt, and 2opt, were doing that. And I implemented that one. Honestly, I don't have any results regarding that one, because heterogeneous VRP is considered to be an exotic variant of the VRP. So VRP in general is considered to be homogeneous, and which holds true to a certain point. I think most fleets in land-based transportation are homogeneous. Right, so these are the results of the algorithm on benchmark instances. These are Christofides instances, if you're familiar with them. So there are 14 of them. The first 5 are just capacitated VRP, no distance constraint. From 6 to 10, they are distance constrained. And 11, 12, 13, and 14, they are clustered instances. So the way the customers are spread over the map, it's a bit different. And the best results I have, are for up to 100, to be honest. So if you see here, for the first instance, actually, the solver could find the optimal solution every time. Out of 10, these are 10 runs. This is the average gap, and this is the best gap. And the first one, it always found the optimum. From that point on, because it cannot make enough iterations, and LNS is not the best algorithm. If you're following VRP literature, you will know that the best algorithm we know is that one of Vidal, the Unified Hybrid Genetic Search. LNS was news about 20 years ago. It still works well, especially if you want to do a small number of iterations. If you have a very fast computer and you can implement the super sophisticated algorithm of Vidal, then you get better results, but still. So for the size of 100, there are decent solutions. To be perfectly honest, this is not a very good solution. So in general, average deviation over 2% is considered not very good. But given the flexibility of the tool and given that it's implemented on a very slow platform, it was considered acceptable. So this paper got published. So I'll tell you at the end where it got published. So once that was done, I decided to move over to facility location problems. Why? Because it's the JS components were there, and if you think of it, facility location problem, you don't need the vehicles, you just need the locations and the distances and durations in between, so more or less the same thing. So I decided to just convert what I have and into a facility location problem solver. The design principles were there, code was there, so I just implemented a taboo search algorithm at that point, which was much easier to implement with respect to large neighborhood search. It didn't take too long. Now I can give you a formulation so that I feel a bit better about this one. So this one does a lexicographic multi-objective optimization. You can decide on the order that you want, but you pick the first one. So essentially, you can either minimize cost or maximize coverage, or there's a third option that doesn't come to my mind right now. I haven't used it in a while. Anyways, so this is the order of the objectives that you set. And then in equation 2, you see that every location has to get service from another location, which can be itself. And constraint 3 says that if you get service from a location, then it needs to be a facility. And constraint set 4 says that the capacity of the facility that you're receiving service from must be respected. And 5 says that you cannot have more than M facilities, and 6 says that if the number of facilities is fixed, or it can be less. And 7 gives you this is the, now I remember, the service distance. So this is the P center objective. So you also want to make sure that it's all equal. So you don't want anyone to get too bad service for the sake of performance. You want to ensure that people who are at the longest distance are also, their distance is minimized. And 8 is distance constraint. So if a facility is too far away from a location, then they cannot get service. That's not allowed if you want to implement this one. And 9 is binary constraints. 10 is mandatory facilities. Sometimes you already have facilities in place, you want to keep them, and you don't want the solver to change them. And the rest of the facilities, they are allowed in 11. And 12 is some locations you just cannot have facilities. Why? They are too small, or they just won't take the investment, or they are not allowed for some reason. And 13 is just the non-negativity constraint for the maximum service distance. Right. So moving over to application of this one, the city I live is called Bath. It has a funny name. I must admit that one. The reason is that the Romans founded it, and it's the only hot springs in all of the UK, I think. So that's where they decided to build their baths. So the name stuck, unfortunately. Anyways, we have one big hospital here. It's called Royal United Hospital. They run all the health services around this place. So maternity is, when ladies need to give birth, and the Royal United Hospital provides ultrasound scans, one around the 2nd month, I think the second one around the 5th month, and then routine checkups is everything is all right, and then the delivery is not in the logistical sense. So we started speaking with these people, and they said that, okay, we have the hospital and we have also 5 smaller facilities. Why? We don't want people to travel too much to the Royal United Hospital every time. They should be able to, you know, get service nearby. Okay, so what's the problem? The problem is that we don't have the money anymore, so we need to shut down some of these facilities. You see, in the UK, the health system is completely based on government. Private healthcare is almost non-existent, and the government healthcare is free. But because it's trying to take care of the whole country, it's overburdened. So they just don't have the money to run it at this point. So they decided to close 1, maybe 2 maternity services. So the map looks like this. RUH, if you can see it on the top left, is the city center. And these are just the assignments to the closest community centers based on the map that we had. And you will realize that for Polton, for example, some of them go to Shepton Mallet and some of them go to Polton. This is because it's based on the fastest path. So by bird's flight, Shepton Mallet may be closer, but actually to get to Polton through the M4, sorry, actually that's M5 motorway, it's easier. So anyways, this is the assignment. And we were given this data, how much was the usage of each external facility. And 1 in Chippenham, 1 in Trowbridge, 1 in Polton, 1 in Shepton Mallet, and 1 in Frome. And we were given also data about how well developed these areas were in terms of level of income and that sort of thing. So they told us how many should we shut down, which was a very strange question. In facility location, you decide on which facilities to open. In this case, they wanted to shut down facilities. Long story made short, we did all the analysis, and they decided on Polton and Frome because they were the least used. Well, the location analysis also showed it the same way. So, but they used it and they were happy with it, and they also kind of propagated it through the NHS network and let other people know that there was such a tool, and they were happy with the results. This also got published. Now, there are 2 solvers that I didn't publish yet, but I want to tell to you briefly. One of them is 2D bin packing problems. For 2D bin packing problems. And the nice part is you don't need GIS data when you're trying to solve a bin packing problem. You just need the dimensions, and then which simplifies things enormously. So whenever somebody wants to use the other 2 solvers, they usually run into some sort of GIS problem. And easier to visualize because there is no map in the background. You can just draw some rectangles and be done with it. Nice thing is you can also solve cutting problems with guillotine cuts, and I implemented a large neighborhood search algorithm with a first fit decreasing constructive heuristic. And the most interesting application, not the most valuable maybe, came from a museum. So this gentleman contacted me. He said, "Hi, I'm working for the Museum of Ethnography in Geneva, okay, in Switzerland. So they were trying to store their paintings, and essentially they have a lot of paintings and they cannot display them all. What they cannot display, they need to store, and they cannot store them vertically. It needs to be horizontal. They need to lay it down. So they had these huge drawers, and they were laying them down in a horizontal way, and they shouldn't overlap each other so that they don't damage each other. But they could rotate them. So it's a perfect 2D bin packing problem. So essentially, and then he said, "Oh, it would be really nice if I could visualize these things." I said, "Well, you can visualize it. There's a visualization that draws rectangles." He said, "No, I want to visualize the actual picture." And I said, "Well, that's an interesting idea. It never occurred to me that somebody would want to put actual pictures on the rectangles. Okay, I'll try to do it." So I did it. It took me a week or so. I sent it to him. Then he had another question, and I said, "Okay, send me your file. I cannot see what you have done." And he actually sent me the file. So these are the actual pictures of what they are displaying at this museum, and it worked well for them in the end. There was also a Canadian company that contacted me. These people have a plasma cutter, and they were actually cutting metal rectangles out of bigger sheets. And this gentleman said that, I want to minimize the scrap, how can I do it? So I gave him a few tips. I don't do this sort of consulting, but I tell them, set the cost of each bin equal to its area, that sort of thing. And he was super happy with it. And he said, the scrap rate is from 5% down to less than 1%, and we're so happy about it, that one. But they didn't write me any letters of any sort. So this is the only thing that I can show you. I think it's a nice picture. So the last one is a 3D bin packing problem. To be honest, I was very intimidated by this one. I was not sure if I could do it because of visualization. So as I said in the beginning and repeated over and over, visualization is the key thing. If you cannot visualize it, the decision maker just won't use it. How could I visualize 3D boxes in Excel? Apparently there is a way, and I'll show you now. And so obviously it's not just about volume anymore. When you move from 2D to 3D, you're putting things into boxes, into containers. CLP stands for container loading problem. So there is also weight. You cannot put too much weight into a box. And it also needs to be balanced. So think of a truck. If you're loading it and the left side is much heavier than the right side, but it's not going to work. You're going to run into a problem somewhere. Why? Because it's going to tip over when it's trying to turn one way or another. And this is more or less the same algorithm I used in the 2D bin packing problem. The first fit decreasing obviously had to be modified a bit, but more or less the same thing. Yeah, so when you visualize it in Excel, it looks more or less like this. So Excel can make 3D boxes, and they can also make them transparent, which is nice. Then I realized if you're solving a one-dimensional bin packing problem, you just need lists, right? So in this bin goes this one, and this one. And if you just check the capacity requirement, and that's fine. With 2D bin packing, you need visualization. Without visualization, when you start giving people coordinates, this has to be the lower left corner. It doesn't work that way anymore. They're not happy with it. They need to see that it works. With 3D bin packing, that's not even enough. I mean, just looking at this picture by itself is not enough. What they need to see is they need to see the animation behind it. Let me share my screen one more time. So you set the number of types of items and number of types of containers, and then you can name them. You can also put the image file name next to it. And if it's in the same directory, it will append the image onto the box. And you need the width, height, and depth. And then you can tell which surface it can stand on and which it cannot. And you can also give them weights. And then for the sake of simplicity, just 10 of each. And just a simple container, 10 by 10 by 20, with a weight capacity that is enough to take everything. And then you see that the design is more or less the same with the pull-down structure, and you can put all the items in here. And once you put something, you need to give it an X coordinate and the Y coordinate as well. So the default is 0, and it visualizes it like this, which you can move around. And then let's just give 10 seconds. And then it looks like this. Obviously, to make more sense, it needs to be animated. So it starts by putting types B. Then you can speed it up by pressing the escape button. And you can get an idea of what's happening. Okay. So this is what I've done. I think I'm on time. Thank you so much for inviting me, and thank you for your attention, and I'll be happy to answer your questions. Just before that one, these are the 2 papers that I published out of the study. The vehicle routing solver got published in Computers and OR in 2017, And last year, 2019, we also published the one on facility location problems with two of my colleagues here in Bath. Thank you so much.